of change. Alright, let's go and look at another example. Let's look at this. Consider an object moving around a circle of radius A. Well, this is the circle. This object is moving around a circle of radius A. This is the radius A. Alright? At t equal to 0, what does that mean? We are now going to observe the object after starting a clock. Now t equal to 0 means at the instant I started the clock, where is the object? The object is here at P. At t equal to 0, the object is at P. A little while later, you can see the object is going to move around the circle. At t equal to 0, the object is at P. A little while later, it is at point Q. So that, I want you to watch here, as the object moved from position P to position Q, what happened to the radius? The radius rotated through an angle theta. And this is the angle theta. That means, as the object got moved from position P to position Q, the radius rotated through an angular displacement. We will represent that by theta. Alright, let's draw a diameter. This diameter is BC. BC is the diameter of the circle. And what I'm going to do is, I'm going to draw a perpendicular from Q so that it touches BC. This is a perpendicular drawn from Q. A perpendicular drawn from Q meets BC at O. Alright? Now take care, take note of all these small developments. Now, O is called the projection of Q onto O. O is called the projection of Q onto BC. The projection of Q onto BC. In other words, if I keep a light over here, the shadow of this Q will fall on BC. That will be the point O. So O is called the projection of Q onto BC. Alright? And now, I want you to follow the motion of this point O as the object continues in its path around the circle. Alright? Listen very carefully. If the center of the circle is the origin, so this is the origin here, the center of the circle. When the object is at P, where will be this projection O? When the object is at P, the projection will be at the origin here. Is that right? If I show the light now here, the shadow of this P will be over here. So, when the object is at P, its projection is at the origin. When the object is at Q, the projection has moved from the origin to that position O. It has moved up. And this distance it moves up is called the displacement. You see that? Why? The distance it moves up is the displacement of the projection. Alright, shall I say that again? When I start my clock, t equal to 0, the object is at P. When the object is at P, its projection is at the origin. And as P moves along the circle, what happens to its projection? It moves up on the diameter. And when the object is at Q, the projection is at O. That means the projection has now moved up through a distance y, and we call that the displacement. In other words, the movement of this point O is going to be exactly the same as the movement of the loaded spring. Alright? This is what I'm aiming at. Alright. Now, when the object is at B, the projection also will be at B. Is that right? You can see as the object continues to move along the circle, the projection O will go up ultimately. When the object is at B, the projection O will also be at B. And what happens as the object continues to move down the circle? Well, Y is now equal to A, the radius of the circle. You see, when the projection is there, this will be the value of Y, which is the same as the radius of the circle. Now, what is the value of theta when the object is at B? Tell me. As the object moves from P to Q to B, the angle theta increases. And what is the value of angle theta when the particle is at B? It will be pi by 2, 90 degrees. Is that right? So when theta increases from 0 to pi by 2, what happens to the displacement Y? Tell me. As theta increases from 0 to pi by 2, the displacement Y increases from 0 to A. Here its value is A, the radius of the circle. Okay. What happens to Y as theta increases further? You can see as the object moves now down the circle, what happens to the angle theta? Watch my little pointer. I'm going to use this as a constant companion for my class. So as angle theta increases from 0 to pi by 2, Y increases from 0 to A, and as angle increases from pi by 2 to pi. Are you understanding this? The angle now increases from pi by 2 to pi. What happens? The projection has now returned to the origin. That means the displacement is now become 0. As theta increases to pi, Y decreases to 0 because the projection will come back to the origin. Y will decrease to 0, and as theta increases from pi to 3 pi by 2. I hope you understand this angle we're talking about. This is pi by 2. Now increases to pi. What happens as the angle further increases from pi to 3 pi by 2? That means the object is now continuing on this part of the circle. Well, the projection O will now move down and approaches the value negative A. And then, as theta increases from 3 pi by 2 to 2 pi, the projection will go back to the origin. Y will increase to 0. In other words, Y will increase from negative A to 0. Okay, the displacement Y is a function of theta. In other words, the displacement of the projection depends on the angle theta. Is that right? One more time. As the angle theta increases from 0 to pi by 2, the displacement Y increases from 0 to A. And as the angle increases from pi by 2 to pi, the displacement decreases from A to 0. And as the angle now increases from pi to 3 pi by 2, the displacement decreases from 0 to negative A. and as the angle increases from 3 pi by 2 to 2 pi, the displacement increases from negative a to 0. So the displacement is a function of the angle theta. The motion of O is similar to the oscillations of the loaded spring, isn't it? The projection that O is now, this is the equilibrium position of the O. It increases to the upper extreme, comes back to the equilibrium, moves to the lower extreme, comes back to the equilibrium. The motion of the projection is the same as the oscillations of the loaded spring. Well, let's say the center of the circle be M. Let's represent the center of the circle by M. Now, MQO, look at this, MQO is a right triangle. Is that right? Because this angle is 90 degrees. Why? Because QO is drawn perpendicular to BC. That means this triangle MQO is a right triangle. The length of the hypotenuse. Can you tell me what is the length of the hypotenuse? MQ. That is the radius. And what is the radius that we call the radius equal to A? So the hypotenuse of this triangle equal to A, and one leg is the displacement. Is that right? This is one leg of that triangle, and that is the displacement. Displacement of what? Displacement of the projection O from the equilibrium position. Can you tell me, what is this angle? What is angle MQO? Any idea? Well, you know that line MP and QO are parallel, and this is a line cutting them. Therefore, this angle and this angle are corresponding angles. They are equal. The angle opposite to y is theta. This angle is the same as this angle. That means this angle is theta. Now, we are now going to obtain a mathematical equation connecting y, the displacement of oscillation, to theta. Can you give me a mathematical equation connecting y, theta, and a? Remember, the distance, the hypotenuse, the length of the hypotenuse is a. In the right triangle MQO, sine theta, look at this, sine theta is opposite side divided by hypotenuse, which is y divided by a. Sine theta equal to y divided by a, and therefore solve for y from there, multiply both sides by a, you get y equal to a sine theta. That means y is a sine function. If you notice here, I have actually traced out the path that will be taken by the projection. The displacement increases to a maximum. When does the maximum occurs? When the angle is pi by 2. Pi by 2 is 90 degrees. When the angle is 90 degrees, the displacement is maximum. And the displacement decreases to 0 when the angle is 180 degrees or pi radians. And the displacement decreases to negative a when the angle is 370 degrees, and the displacement increases to 0 when the angle is 2 pi or 360 degrees. Can you figure out this graph? What is the function? What function has this kind of a graph? Well, this